Okay, for this homework video, we're doing 9, 21, and 37. Exponential equations, what we want to always look for first is one-to-one property, and then if we can, we're going to natural log both sides. We also have the option of putting into logarithmic form from the exponential equation form. However, the first two methods of first looking for one-to-one property, and then secondly, if we cannot get the same bases to set the exponents equal, then we're going to natural log both sides. So that's what we're going to try here. So I look at 32 and 8, and I go, okay, can I get those two as the same base? Well, our factor or exponential outputs for 2 to the first, 2 to the second, 2 to the third, and so on. 2 to the third is 8, and 2 to the fifth is 32. So we can actually get these to be the same. I'm going to represent 32 as 2 to the fifth, and that's taken to the x power. And then we have 8 is 2 to the third. So now I look at this and I go, okay, those exponents are equal. 3 over here is going to be equal to this. Well, if we have a power taken to an exponent, that means we multiply the exponents. So that equals 5x. And now this is a basic linear equation, divide by 5, and x is going to equal 3/5. Next one, again, we're going to see if we can get like bases. And this is definitely possible here. We both can get a base of e for these. We already have a base of e here. Here we have e in the denominator, but we know if we flip the base, that flips our exponent negative. And now since our bases are the same, we have one-to-one property, so we can set the exponents equal. I'm going to subtract over 1 to solve for x, and we have x equals -2. Last one, this problem, I definitely don't think that 410 is some exponential form of 7, like 7 to the second, 7 to the third, and so on. It isn't. So we don't have one-to-one property applying here, so therefore we're going to try natural logging both sides. When we natural log both sides, the exponent comes in front, so we have x plus 2 natural log 7 equals natural log 410. Note that's our power property rule, where if we have an exponent in the argument, that exponent can come in front of the logarithmic or the exponential term. Of the logarithmic term. So now we look at this and we have x is right here, that's what we want to solve for, and this right here is a constant, but when we multiply it in, we do have to think about it like as a variable in terms of combining like terms. So we have two options here. We could divide both sides by natural log 7, and then we'd subtract over 2. That may, I think, let's go that way, and then the other way would be distributing and then solve for x. So first thing I'm going to do is divide by natural log 7. And when we do that, we get x plus 2. Note that's just anything over itself cancels. And then here we have natural log 410 divided by natural log 7. And now we see if we get the 2 to the other side by subtracting 2, we get x equals that. Of course, you could plug that natural log divided by natural log in your calculator and then subtract 2 to get the answer in estimate form or decimal form if it asks for it. Now, second method, coming back to here, the other way you could have gone about it and said, okay, if I distribute this in, now I have the x term, x natural log 7, as I indicated in class. If you're not my student, your teacher probably indicated as well. It's preferable to write the natural log term after the variable or after other terms, because if you write x after it, like natural log 7x, like so if I wrote it like this, it now looks like x is a part of the argument. Even if you put a multiplication sign, it's still unclear. If we then put parentheses around both or one of them, it would, or definitely around the natural log 7 at least, would be more clear. But nonetheless, if we write the natural log term second, it's quite clear that x is not a part of the argument. So that's the agreed upon and accepted method for writing a variable or a term when it has a logarithmic expression like natural log 7 in it. So now when I distribute the natural log 7 to the 2, that would be plus 2 natural log 7. Once again, we write the natural log term after it. And now if we look at this, this right here is our variable term. This is like 2x, right? This number right here is a number. So if I have number times x, you can think of this in simpler terms like 2x or 3x. And we also have a constant over here because relative to the variable, there's a constant. We don't have an x in here. So this is like 2x plus 4 equals 8. We want to move this term over and then divide by that. So that's what we're going to do. We're going to move this term over. We're just going to subtract all of it. These cancel. And now I'm just going to rewrite what I have left on this side, which is the x natural log 7. Over here, I think it's fairly reasonable to write the positive term first and the negative term second. And now we have on the left-hand side x times some number. And if we have x times some number, to undo that number to the other side, we're going to divide by that number. And if we look here, this would be our final answer right here, x equals that. Note, it does look different than what we had up here, but if we multiply this by natural log 7 over natural log 7 to combine this into one fraction, we would get the same thing. So either way works, but our answer in the end looks a little different if we don't do fraction combining. And that's it.